All right. Still another coin problem. Yeah. Coin in a row. So that row is important. Okay? Yeah. So why the row is important? There is a row of n coins whose values are some positive integers, not necessarily distinct. Okay? So if C, I, C, J equal, it is okay. Okay? Yeah. The goal is to pick up the maximum amount of money. Maximum, yeah. You know, people always want to, you know, get maximum value. Yeah. But there is a constraint. Subject to the constraint that no two coins adjacent in the initial row can be picked up. If you do not have this constraint, then everyone pick all the coins, right? Then it's too easy. Yeah. So we like to put some constraint to make the problem a little harder. Okay. If you pick C1, then you cannot pick C2. Okay. Then you can pick C3, but if you pick C3, you cannot pick C4. Okay. So you have some constraint you need to follow. Under that constraint, what is the best solution? The maximum value of selection of the coins. Yeah. First, let's do mathematical representation. Yeah. The total amount of money of the coins we pick. Here we use subscript, special subscript, CI1, CI2, CIK, because we can jump. Okay? Yeah. So we cannot just use 1, 2, 3. Yeah. We cannot use adjacent. So we need to use some notation that allow us to do jump. Jump. Okay? All right. So that's why we use this notation. All right. Then how do we specify? How do we describe that constraint? No two adjacent coins are selected. Okay? So here, let us assume these subscripts are in increasing order. Okay, how about that? C1 less than I1 less than I2. Yeah. Let's assume that this condition. Okay, increasing order. All right. Then no two adjacent coins are selected. We translate into this. Ij minus 1 greater than 1. Then no two adjacent coins are selected. If equal 1, then adjacent. Yeah. So we do not allow that. So we make greater than 1. So no adjacent two coins are selected. Yeah. So you can see. Yeah. All right. That's the condition. Yeah. All right. Then under that constraint, what is the maximum value of Sm? Yeah, this is still an optimization problem. And for this one, we know it is hard to use the greedy algorithm. Yeah, greedy, you know, when we make decision, we try, yeah. So for example, the greedy, yeah, we can do greedy easily, but the problem is the greedy algorithm does not guarantee it is an optimal solution. Okay, let me use the greedy. Greedy, we can have many strategies. Let's use this strategy. Let's pick C1 first to be greedy. Then we cannot pick C2. So then C3, okay? Then C5, and so on. Okay? That's based on the greedy strategy. Very easy, right? But you cannot guarantee this is the best solution. This gives you the maximum. This cannot guarantee the value is maximum. Yeah, so that's why the greedy algorithm does not work for this example. Yeah. So we use a dynamic programming. Yeah. Divide problem into subproblems. that recurrence relation. If we can do that, we solve the problem. Yeah. All right, now the constraint. No two coins selected can be adjacent in the row. Yeah, the main constraint. Yeah. How do we enforce this constraint? Yeah. When we consider our subproblems, we need to use this constraint. Okay? Yeah. Go. Find the maximum amount of money subject to the constraint. Our goal. Okay. First, we need to define a subproblem. Yeah. What is a subproblem? Okay. A function. You need to define a function to describe a subproblem. Okay. Here, the function we call it f of n. F function, f of n, with variable n. N, the number of coins in the row. Okay, Fn. What's the meaning of this function? The maximum amount of the money, maximum amount for the row of n coins, number of coins, n coins under the constraint. That's it. The straightforward way to define the subproblem. Sometimes we can use the straightforward way to define. Sometimes it is hard to define a subproblem, but sometimes very easy, just the straightforward way. So here it is easy, straightforward way to define subproblem. Next, recurrence relation. We want to consider the relationship between two adjacent subproblems. Okay, yeah. Single piece reduction. Single piece reduction. Here, one piece corresponds to one coin. Okay, yeah. Same as our previous example. Consider the cases with and without Cn. So here, that piece, the last coin, we consider reduction of the last coin. That piece, that's the piece we consider. Okay, all right. That reduction. That reduction, so we consider two cases, with case, without cases. Yeah. Because when we try to get a solution Sn, is the optimal solution contains Cn or not? Both possible, right? Both cases possible. So there are two possible cases. One case, Sn contains Cn. Another case, Sn does not contain Cn. So we just consider those two cases. Okay? Yeah. All right. Case 1. Select Cn. So that means Cn is included in Sn. Yeah. Case 1, Cn is inside Sn selection. Okay. Then, based on our constraint, Cn minus 1 cannot be selected. So here we enforce that constraint here. Okay. In this situation, let us write the f of n function. What is f of n? Because if you cannot contain Cn minus 1, you can only consider the remaining coins in your Sn, right? Now, what is the best solution for the remaining n minus 2 coins? Right? You need to consider that subproblem. Okay? Based on our notation, that solution is f of n minus 2. That is the definition of the subproblem. Okay? The value, the maximum value for the coins in a row, you only use the first n minus 2 coins. So you get that value. But remember, you also have the Cn value, right? Plus. Okay? So the equation is this. Under this our case 1 condition, the relationship is f of n equals Cn plus f of n minus 2. This equation. Okay. But this is the first case. We have the second case. Cn is not selected in Sn. Not selected in Sn. Okay? Yeah. That's possible. So we need to consider that. Okay? All right. But when Cn is not selected, then Cn minus 1 can be selected, right? So then all the first n minus 1 coins can be selected, right? What is the best solution? Yeah. We have the definition of the subproblem. The best solution, f of n minus 1. Okay, so that is, in this second case, f of n equals f of n minus 1. Right? Now we combine the two cases. Yeah, you need to combine all the possible cases. If we combine these two cases, we get the overall equation, the maximum of these two possible numbers. Yeah. We only consider these two possible numbers, so you pick the larger one. So you get your recurrence relation. So this is our recurrence relation. After you get this recurrence relation, right now we treat the problem is solved. Because the implementation, we know how to do implementation easily. Right? Yeah. So we treat the problem is solved. Yeah. All right, so this is 8.2.